Okay, let me hide meeting controls. Is ready, Sketchpad is up, and all right, so why don't we begin? So good morning. This morning, 4 o'clock, my daughter woke up vomiting. So it's been quite the morning so far. So hopefully I remember everything I had to say. Um, if you are, yes, some of your colleagues contacted me. They're joining online for various reasons. So this is being recorded. So if you are online, please mute your video if you choose not to have your likeness recorded. So I'll give you a few seconds to do that. Okay. All right. So why don't we get started? So good morning. Happy Monday. Hope you had a great weekend. Today, we will finish up with so-called discrete distributions, and we'll pivot to important class or family of distributions, namely continuous distributions. And so I have a bunch of stuff on the board that'll make sense when the time is right for module lecture 19. All right, so we'll finish up with a Poisson today. And then with the balance of the time, we will get to as far as we can get with continuous distributions. Okay, but before I begin, excuse me, the usual administrative bits, the reading has not changed. And the reading, again, is purposed with giving you that book modality to read about these distributions. Just about any statistics book will do. I'm a fan of free. Hopefully you are too. The material is hundreds of years old, and just about any stats book will do. The difference is really just how it resonates with you, right? So please don't limit your sources to just what I have on the Moodle site. That is just one source among many sources. Fantastic sources, the Khan Academy series on YouTube as well. Okay, project number 4, which is the project part, excuse me, of the New York City taxi problem. And I'm scoring the written part of that as homework too. So any questions, concerns? Um, Pointers? No. I've spoken with the TAs about a little bit about some of the parameters of the project, as well as types of hints that they should give you and things like that. And so you'll notice this project, the data set, is a little bit messy, right? And you spend a bunch of time dealing with the data dictionaries, which I took time on purpose to go through to try to understand the data values, the variables, the values, and then you have some other decisions to make with a lot of nuances, such as the vendor ID for the transponder. If you have a knotted number entry, you can't just replace it with the mean, right? Because these IDs, 1 or 2, they're meaningful, right? And they have to be 1 or 2. They can't be like 2.35 or 1.35. Okay. So this sort of messiness is very typical with data sets you encounter in the real world. And just as we introduced it, as I understand, the NYC Taxi Limousine Corporation released January 2023's data set, right? And that's sort of par for the course. You don't have control over when the organization that owns the data, when they release that data. Why are they behind 2 months or 1 month if you count end of the month, February, because March hasn't ended yet? I'm not sure why, but their concern is to collect these data sets for their own purposes, and we're just wrangling, using them, and transforming them for our purposes. Okay. Any questions about it? No? How about the question formation? And we could spend an entire semester, and many disciplines do, but we could certainly spend an entire semester just on so-called sample design. And for disciplines like education, sociology, psychology, they usually have courses that go over various concerns for both when you construct your data set as well as when you design your own data set. Computer science, for I don't know why reasons, we don't have a course like that. I was very fortunate when I was in grad school at UMass Amherst that we had something called empirical methods for computer science, which was sort of that type of course for computer science. But the person who taught it, Dr. Paul Cohen, his undergrad was psychology. So it was one of those things that he wanted to bring to computer science. But if you're interested in experimental design, the disciplines that traffic in that quite readily, urban planning does, or they should, but certainly social science, sociology, psychology does that very regularly in their curriculum. And I don't know if do they have that in their curriculum here? Experimental design? No? Anyone know? All right. Okay. So that being the case, let's jump right in. As of today, after today, we have 5 more weeks left in the semester. And as I said last time, we're going to be pivoting rapidly into the modeling aspect, which will be our gateway to the extraction of insights, specifically looking at machine learning methods and taking a look at the implementation of these methods for extracting insights from data from the scikit-learn API, primarily in Python. Any questions? No? Okay, everyone's really quiet. It's Monday morning. All right, I hear you. So where we last left off, we motivated what I like to call the Poisson configuration. And with this, we look at discrete random variables, those variables that traffic in countable quantities. And we looked at the arrival of some event in time. And in our depiction, each observation is represented as one of these dots, or in electrical engineering, they use to say meatballs. We have our window of time, delta t. And so this observation could either result in an event occurring or not occurring within this module or window of observation, this time period, delta t. And we said the only requirement for this delta t is that it be consistent across the progression of time. So delta t could be every minute, it could be every millisecond, it could be every 15 minutes, it could be every hour, every week, every year, if you choose. And so of interest in time-based systems is this idea of the average occurrence over all time of an event happening. And so we call this the rate. And for many, a problem of interest is whether or not a particular set of observations in our temporal window occurs, and there are probabilities associated with it. So this rate occurs in each delta t, and sometimes in the literature you'll see synonyms, module or window of observation, but it all refers to the same thing, this delta t. And when you're designing your model, your mimic of this time-based system, it's important to define what your delta t assumption is. Okay. And so then we said some examples, and that's where we left off last time, some examples of systems that traffic in events in time. And it isn't limited to this. I'm sort of struggling to speak this morning from being up 4 o'clock when I didn't want to be or choose to be. But we have a retail concern. And in a retail concern, you're interested in a number of customers that arrive in time. They walk into your store. And in this case, this event that occurs is the presence of a customer. So for example, in your first 15 minutes of operation, let's say you're a coffee shop, you might have 5 customers walk into the store. That's the occurrence of 5 observations, the event customer arrival that happens in one 15-minute delta t period of time. Another one could be students who visit the dining hall. Absolutely, they record the card swipes, and they can be, it's not hard to do, timestamped. So absolutely, you could record for every hour of operation for the dining hall, how many students swipe in. That's another system that's well modeled by this so-called Poisson distribution. And then this last one, it could be ITS, looking at the amount of network traffic, packets of data that go across a network at some period of time. And so for this, they're typically going to have it packets per second, because for high bandwidth networking, gigabit I can't do the calculation in my head. I think it's 10 to the 60 or 10 to the 40, 10 to the 60, I believe, or I'd have to look back at it, but gigabit networking traffics rather in several billions of packets per, well, not packets, of hundreds of millions of packets per second going over a high-speed router. And so each of these are well described by the Poisson distribution, and why you care about modeling probabilistically these sort of systems is you might want to do forecasting or projection to help you plan your capacity. Planning your capacity in the case of, say, a dining hall or a coffee shop could mean how many employees you're going to hire for that shift. And for a router, it's going to help you plan how much router memory you're going to install on your routing infrastructure. And router memory, if you didn't know, it costs tens of thousands of dollars. It's a very expensive thing. It's not the same memory that you would buy to upgrade your laptop. Okay, any questions about this? Does that make sense? And so for this projection, you're setting up your model, you're replacing a reasonable estimate for population parameters into your model based on what you select. And then you're sampling from your model and you're asking it questions based on the data that your model produces. And this is a lot better than just kind of back of the envelope saying things like, I'd like to have maybe 10 employees for the morning shift. That's the easiest way to go bankrupt if you're an enterprise, because the worst thing you can do is have more employees than you need on a particular shift, because for any enterprise, employee cost is usually the largest line item on the balance sheet. Okay, any questions about this? All right, now I'm awake. Okay, good. So let's continue on with the Poisson distribution, and let's define as K the number of occurrences of interest. It could be K equals 3 customers came in this 15-minute period. K equals 10 customers that came in that 15-minute period. And then let's define R to be the rate, and this rate is the average number of observations continually over time. And so what the ask is for the Poisson distribution is, given a particular average rate, what is the probability during some window of observation you're going to see K many of those events arrive in time? Does that make sense? Any questions? No? All right. And so this is the probability mass function for the Poisson. Probability of observing K many arrivals or K many events is equal to the rate exponentiated to the K upon K factorial upon E to the rate, where E is Euler's number, okay, or Euler's constant. Now you look at this, okay, we're not done, but what in the world does this mean, right? Bless you. What does this mean? Where does it come from? And this is one of those cases where there's this absolutely beautiful relationship between the binomial distribution and this construct. And then, as we talked about before, the binomial distribution is nothing more than a sequence of n many Bernoulli trials. Now, this happens all throughout mathematics. And the reason for that is, if you're going to come up with something new, it's kind of nice to use the tools you already have, right? Why reinvent the wheel? It makes obvious sense. And so if you never become a math major, I strongly encourage you to read books on the history of mathematics, because it'll walk you through all these interesting oops moments and all these interesting reuses of earlier tools to build new tools at the time when it was developed. Okay, and so let's recall the binomial distribution. And in mathematical notation, you say let your random variable, in this case big X, and you have this tilde, this squiggle, be distributed as, is how you pronounce that. So we have random variable X is distributed as a binomial distribution. And then this binomial distribution has two so-called parameters, numerical characteristics that define the structure of this type of stochastic system. And N is the number of trials, and P is the probability associated with the success state. And so in this case, for the binomial, to jar your memory from last time, talks about the probability that you have X many successes out of N trials given a success rate of P probability. Does that jar your memory? Make sense? Yeah. Okay. So what is this relationship? Okay, let's unpack this. And so this is the probability mass function, the probability for the binomial distribution. We have n choose x, so these x many successes are scattered among the n many trials, and it's without replacement, choosing one of these n many slots for the success, and the arrangement is indistinguishable. So it's choose. So we have n choose x, and then we have x many successes. So we multiply p, the success rate, by itself x many times. And then we have the failure rate for the remaining n minus x trials. So we have 1 minus p, which is abbreviated as q, exponentiated to the n minus x. So we have the number of arrangements of the successes, followed by the probability of the successes, followed by the probability of all of the failures. Okay. Any questions? Make sense? All right. And I forgot I have my digital pen here. All right. And so the expectation we said, the population mean of a binomial distribution is equal to NP. And that kind of makes sense. If you have n many trials and the rate of success is P proportion or probability, then you multiply n by P, and that's on average how many are going to be successes. Okay. So this is our average number of successes. And this average number of successes, if we think about this idea as a success being the arrival or of an event in time, this average rate of success kind of looks like our average rate of event occurrence in our temporal sequence. So this sounds a lot like the rate, because if the average number of successes over time is large, that would correspond to a high rate, 100 customers per minute. If the average number of successes over time is small, that would correspond to a low rate, 3 customers per second. Does that make sense? Okay, any questions? No? And so this sounds a lot like our rate, which it is, but there's a little bit of a problem here. The binomial distribution, we said, talks about n many trials. How many of these, the probability, what's the probability associated with x successes, but this trial number for the binomial distribution is n. Okay, we have a solution for that. And so let's assume this np for the binomial distribution is exactly equal to the rate. And so we're gonna, let me bring up the pen here. If that's the case, let's go ahead and let's equate the two. So we say NP is equal to R. I'm a little bit rusty with the pen here. And if you hadn't noticed, I'm looking at the screen, but writing without seeing where I'm writing, right? So it takes some practice to do this. So we set NP equal to R. We do a little algebra. And now we have a closed form expression for our probability P. Probability P is equal to R upon R upon N, our rate, and divided by the number of trials. And so we can take our expression for the probability mass function for the binomial distribution, and everywhere we see P, here and here, we can substitute in rate upon the number of trials. Does that make sense? Any questions? No? All right. So now let's go ahead and let's do that. And so now the form of our probability mass function for the binomial distribution is equal to n choose x. Well, that hasn't changed. We have r upon n to the x power. Okay, that used to be p to the x power. And then we have in this last term, our third term, 1 minus r upon n to the n minus x, where this r upon n, that used to be p. So now that we have this substitution for p, we're going to go back to this problem that I talked about. This nixing thing for the binomial distribution is this idea of n, the number of trials. Now, of course, when we talk about events in time, it doesn't fit to say the number of trials. So how do we get these two things to correspond? Okay, well, When something happens over time, how much time do we assume? We didn't make a definition for it. So let's say time gets really, really big. We can assume every single possible moment of time over which an event occurs, every single moment's really, really big. Okay. So let's make it really big. You see an observation at every possible moment of time, or you don't see an observation. Okay. And so that means we need to make n, the number of trials, really big. We can do that by assuming it is infinite. Okay. And so now we can take our new expression for this binomial distribution and express this idea of any moment in time. Because any moment in time, we say the number of trials n is equal to the first one, the next one, the next one, the next one, infinitely many. Does that make sense? Any questions? No? All right. So if we do that, we're going to use limits. And we're going to say, okay, let's take this expression or modified expression for the binomial, and let's let n get really, really big. Let n approach infinity. And then we're going to observe and rewrite mathematically what this expression becomes when n gets really, really big. Does that make sense? Any questions? No? All right. So a property of limits is that if you have the limit of an expression, and we'll examine our modified expression, it's this entire thing. Between the brackets, we have three terms. It's the product of term one, term two, and we'll call this last term, term three. Anytime you have the limit of the product of a bunch of functions, in this example, we have two functions. We're going to call the first one f of x. That's like saying term one. The second one, some function g of x. That's like saying term two. Whenever you have the limit of the product of two terms or functions, that's the same as the product of the limit of the individual functions. So here's the limit of term one, and this is like horrible notation, and here's the limit of term two. So in that case, we have three terms, term one, term two, and term three. They're multiplied together, and we take the limit of that product. That's the same as the product of the limit of term one, the limit of term two, and the limit as n goes to infinity of term three. Does that make sense? Any questions? No? All right. So now let's do that with the first term. So we have the limit as n goes to infinity of n choose x. And we know from before, when we talked about combination, we said, and I'll write it up here, n choose x is equal to n factorial upon n minus x quantity factorial. And then we have an x factorial, okay? And when we expand out this term, we get a cancellation up top, and this n minus x cancels out. And then we're left with a set of terms, x many terms in the numerator and x factorial in the denominator. And whenever you multiply terms, it's like going back to, I don't remember when they teach it, when you come up with a polynomial and you multiply terms together and you get a polynomial. Here, when you multiply these terms, n times n minus 1 times n minus 2, all the way up to and including n minus x plus 1, here you have x many terms, okay? And whenever you multiply those x many terms, you're going to get some polynomial. That polynomial is going to have a degree, a largest exponent of x. The reason for that, and I'll just show you here, here you have n times a quantity that includes n, times a quantity that includes n, times a quantity that includes n. So the first term is going to be n times n times n times n, x many times. And so that leading term is going to be n, in that case, raised to the x power. And then coming later are other terms in that polynomial where the exponent is less than this x. Does that make sense? Okay. So here's an example. If we had n minus 1 times n plus 2, we multiply the first terms, that's n squared, Outside, that's plus 2n. Inside, minus n. Last, minus 1, 2, that's minus 2. And so 2n minus n is n. That's equal to n squared plus n minus 2, if I did that right. You'll notice here, the highest power, the degree of that polynomial, is 2. I'm multiplying one term, two terms together. Every other term, the exponent, is less than the number of terms. Does that make sense? Any questions? No? All right. So we know this is absolutely the case when we multiply out the numerator resulting from n choose x, and we're going to get this polynomial. We have n to the x power, and then we have the addition or subtraction of other stuff that are less than n to the n that are less than n to the x, excuse me. And then we have that in the numerator, and then the denominator is our x factorial. So what happens when n gets really, really big? That n goes to infinity part says, okay, we have something that's really big exponentiated to the x power. And the difference between that and all the other terms is another multiplication less, or it's an order of n much less than that first term. And so what ends up happening if n gets bigger and bigger and bigger, for the value of this polynomial in the numerator, the stuff that's less than n to the x, it's not going to matter very much. If n, for example, were 1 billion, and you can even, try that exercise, 1 billion to the x power plus 1 billion to the x minus 1 power, that term to the x power is going to overwhelm all of the other terms in that polynomial because the exponent is bigger. Does that make sense? Any questions? All right. So mathematically then, if we take the limit as n goes to infinity, n gets really, really big for this expression, we can just drop altogether the stuff less than n to the x power, because that's what's going to dominate as n gets bigger. So we can rewrite this legally as n to the x power, because the other stuff doesn't matter, upon x factorial. Does that make sense? Any questions? No? All right. So now we took care of the first term. Now the second term, r upon n to the x power, we're just going to leave that as it is. So we said at the outset that the limit of a product of terms is the same as the product of the limit of terms. So now we're going to put together that limit of the first term with as a product multiplied by that limit of the second term. So we said we n to the x plus stuff less than n to the x upon x factorial, and we have r to the x upon n to the x, okay? And we said when we took the limit, we dropped the stuff less than n to the x. So this gives us n to the x power upon x factorial, for that first term. Second term, r to the x upon n to the x. Oh, wait a minute. I have an n to the x in the numerator here, the denominator there. They cancel, they go to 1. So that leaves us with 1 times r to the x upon x factorial. Does that make sense? Any questions? No? All right. So now we know we can change this limit to be r to the x upon x factorial. And what this limit represents, to jar your memory, is that we're considering a success or failure to be the occurrence of an event or non-occurrence of an event for every single possible moment in time. Okay, so we took care of the first two terms, the product of the limits. Let's take a look at that last term. Okay, so for that last term, we have limit as n gets really, really big of 1 minus r upon n to the n minus x power. All right, well, if we look at the exponent, we have a negative exponent. We have n power and we have a minus x power. Negative exponent is the same as 1 upon that quantity to the non-negative exponent. And so if we do that, okay, what we have is the n part, 1 minus r upon n to the n power. That's this first part here. And then this minus x, we get 1 upon 1 minus r upon n to the x power. Okay. And so now we're going to take a look at our limit. and we make the observation here on this r upon n in the denominator. We have n r upon n. As n gets really, really big, well, any value r upon something really, really big, it's going to be effectively zero, right? So as n goes to infinity, we say r upon a really big number, that's just 1 minus 0, which is 1. And 1 raised to any exponent is always 1. Okay? So we make that observation, and that term goes away, it goes to 1. Does that make sense? Any questions? No? Yes. Mhm. It's That's a great question. It's literally just a partition of time. And the data is just, did it occur or did it not occur? And so if, two students walk into the classroom, and let's say my delta t um is 5 minutes, right? This 5 minute period, how many times did I see someone walk into the classroom? This next 5 minute time, how many times did I see someone walk into the classroom? And so delta t is this partition in time, and what you're counting is a success or failure, like flipping a coin every moment in time. And when it comes up as a success, that corresponds to the occurrence of an event. When it corresponds to a failure, the event didn't occur, where event is student came into the classroom. Does that make sense? Yeah, okay. Any other questions? All right. And so whether you want to know, did the students come in at, 8:45 or 8:46, right? That's a function of how big or how small you make your delta t. It'll tell you how many in the window of observation, what's the likelihood. But if you want down to the millisecond, right, you have to define your delta t smaller. Does that make sense? Yeah? All right, great. Thank you for your question. So we now have limit as n goes to infinity of 1 minus r upon n to the n power. And I'll just have you take this on faith. Whenever you have 1 minus r upon a big number, and you take that quantity, exponentiate it to a big number, that's the same as Euler's constant raised to the minus r power. Don't believe me, the proof is out there. Oh, that's not Moodle, I should say Canvas. I'm so used to saying Moodle. I will post a source on course resources section of Canvas. What is E, right? And it expands very beautifully about what Euler's constant is. Okay, but right now, take it on faith. If you don't believe me, and I hope you don't believe me, I'll certainly post the source that will explain why that is the case. Okay, if you're interested in that. Okay, any questions? Does that make sense? Yeah. All right. So now we have e to the minus r for a third term. Okay, and we put it all together. We have r to the x power, our rate, upon x factorial times e to the minus r. And so this is exactly the mass function of the Poisson distribution, what that probability is of observing k events given an average rate of r. Okay. So now when you see it written, you'll say e to the minus r, or you see it how we have it at the inset on the bottom left, your left of the screen. Now, they often replace r with Greek letter lambda, the quote unquote rate parameter of the distribution. And why do they replace it with Greek letter lambda? Because it looks fancy. Okay, and that's all. And any questions about this? No? Make sense? All right. And so the Poisson, which traffics in time, talks about the probability, and that's the mass function, associated with observing X many events in a window of observation delta t, given the average rate lambda over all time. And you can absolutely calculate this from data. All right. So that is it. Any final questions? No? All right. And so when we look at the population mean, mu, of the Poisson distribution, or so-called Poisson random variable, the population mean, mu, is just lambda. And the population variance, sigma squared, is also lambda. And I remember back in grad school, it's a stupid math joke, but why is the Poisson mean and variance the same lambda? Because it didn't take mathematical statistics at UMass. It's not usually the same. All right. Anyways, that didn't do very well. Okay, and so the derivation is there if you wish. There's a URL on YouTube. It's about 19 minutes, and I stress this isn't the only source for this material. It's actually quite old, right? I encourage you, if you're interested in looking at the derivation, that you find a source that resonates well with you. Okay. Any last questions about the Poisson? No? No, I'm struggling to say, is it Poisson or Poisson, right? But anyways, I digress. So that's all we had for the so-called discrete distributions. Let's pop out of the share because every time you stop PowerPoint, it's not guaranteed to preserve the share. Let me tear down the slide, keep annotations, and let me reshare the new slide deck, which is 19. So let me get rid of that. Save. All right, there we go. So that's 19. All right, so let me bring Zoom to the fore, share screen, and that's 19, share, and then screen slideshow. There we go, down here. And then you're not seeing what's on my screen. I need to do one more thing, use slideshow. And all right, great. So nope, I don't want to do that. Hide meeting controls. Meeting controls, time check. Okay, we have a good amount of time. All right, great. So let's pivot now to the so-called continuous distributions. And in order to talk about continuous distributions, we'll refer to the stuff I've written on the board, and we'll talk about what real numbers are and special properties of them. And so I won't go over the administrative stuff again, since we did it already. When we talked about populations, or rather distributions, as being a type of law that governs the occurrence of data, we then talked about so-called distribution families, and the families we talked about up to this point are a sampling, no pun intended, of the so-called discrete distributions. And these discrete distributions travel in countable or finite quantities. When we look at the Poisson distribution, we're looking at the number of occurrences of an event. 3 students walk into the room, 10 students walk into the room. For each one of those quantities, that's a count. You can draw one-to-one correspondence with what you're talking about and the natural numbers. And that's the case for Bernoulli, success or failure. It's one thing you're talking about, true, false, you can count that. The binomial, it's X successes in N trials. You can count that. And so all of the discrete distributions are so-called countable. They're either finite or you can draw one-to-one correspondence with the naturals. And so we're going to pivot now to real valued quantities, and that's the domain of so-called continuous distributions. But we need additional tools in order to talk about them. And I really, really hope, if you're thinking of graduate data science, I really hope you do, I really encourage you to take a so-called mathematical statistics course. Okay, so we talked about the Bernoulli distribution, and the Bernoulli distribution corresponds to systems whose stochastic behavior is described by a two-way outcome where there's a probability assigned to each one. Okay, then we took this Bernoulli distribution and we arranged them in a sequence, n many slots wide, and then we asked the question of the probability that X of these sequences among the n are going to correspond to a success outcome. Now, of course, the other requirement for this binomial, this sequence of Bernoullis, was that each of the trials is independent. You're not going to change the probability from one sequence, one trial to the next based on the outcome of another trial. And then we took this Bernoulli and we made a stylized sequence where you have failures that end in a single success. That's our geometric distribution. And so again, we see this Bernoulli distribution being reused. And an example that's modeled well by a geometric distribution, and I'm going to say it right, if you have a player in basketball with a certain free throw percentage, that is your probability of success for making the basket. And you make shots, and the question that the geometric is asking is how many shots do you need to make, how many tries, in order to get, say, 5 baskets, right? And as you can imagine, if the free throw percentage is bigger, it's a higher probability. You take fewer shots to get 5 baskets. If the free throw percentage, and I cannot say that without thinking, if the free throw percentage is smaller, that probability is smaller. And as you can imagine, it's going to take more shots in order to make, say, 5 baskets. Any questions? Does that make sense? And so the problem then becomes not studying in detail all of the systems that you're trying to model. It's matching up the properties of the model with each of these families of distributions. Okay, does that make sense? Any questions? No? All right. So then lastly, we talked about the negative binomial. And the negative binomial, instead of talking about the probability of the number of successes in a fixed number of trials, it talks about the number of trials or tries in order to get a fixed number of successes. And the important thing to pay attention to with a negative binomial is, yes, that's the theory, but when you look at the API implementations, it's really important to understand what they're measuring. Because in many implementations, including in the default Python library, the negative binomial, especially when doing sampling, is the number of failures, not the number of trials ending in a success. And so in that, if you want to talk about the number of trials, including the success at the end, you have to add 1 to that sample. And so that's just one of those cases where, for whatever reasons, the team that implemented this library for sampling from a negative binomial chose to only count the number of failures. Okay. Any questions? Does that make sense? Yeah. Okay. And then lastly, we talked about the Poisson. Poisson is a special case of the binomial where we let the number of trials, n, go to infinity, because now we're talking about every moment in time. Okay. Any questions? Does that make sense? Okay. And so let's pivot to this measurement of quantities. Now, things in the real world are messy, wonderfully so. And when you model them, it's very messy and a lot of interesting issues that you have to deal with. But from our human experience, we're used to things like pressure, time, temperature, distance, velocity, and acceleration. Now, all of these quantities are so-called inertial. And what inertial means is that at any moment in time, the next instant, the value of, say, temperature has a lot to do with what the current temperature is. Temperature just doesn't instantaneously jump from 35 degrees to 70 degrees. That'd be weird, right? 30, 70, 30, 70. You'd be like, what's going on? It doesn't happen that way. Likewise, position. I can't walk from here to there, take a step, next instant, I'm over there, right? You'd be freaked out, like he's like a Highlander or some sort of shapeshifter. So it doesn't work that way. So all of these so-called physical quantities, they're inertial, yeah, but they're also described by so-called real number, okay? So we need to, if we're going to model a system that traffics in these inertial or physical quantities, we need a way to talk about probabilities involving these. But something weird happens, and let's talk about that. Let me ask you, how many values are in the set of real numbers? Can you identify the individual values like you can in the naturals? No, you can't. If I tell you, okay, 0.001, what comes next? 0.002? No, there's a lot of stuff in between 0.001 and 0.002. Okay, so there are an infinite, more correctly, an uncountably infinite number of values in this set of real numbers. And what that means is that this sort of infinity is different. It's different from the natural numbers. The natural numbers, yes, it goes on to infinity, but at least you can identify the individual elements of that set of numbers. There's the 0, there's the 1, there's the 2. You can do likewise with the integers. You have 0, positive 1, negative 1, positive 2, negative 2. You can absolutely identify them. But in the reals, it's different. This sort of infinity, in a sense, is bigger than the type of infinity that we talk about with the natural numbers. It's so big you can't even identify the individual members of the set, okay? That presents us a real serious problem when we're trying to talk about probabilities, because if we're trying to model, it'd be kind of nice to be able to say, what's the probability that it's going to be 50 degrees? Okay. We still need to enterprise to be able to do this. Okay. So here's the real number line. And because I can't identify them, I'm going to mark the integers going off in the negative direction and the positive direction on the real number line. Okay. Now, these are countably infinitely many. As I said before, you can say there's 0, it's one element, then 1, then -1, then +1, then -1, +2, then -2, and you can keep going. Okay. So these are countable. Okay. Now let's decide we're going to take the interval because you said wholeness. I don't believe you. I don't believe you that I can't identify the individual elements of the set of reals. Okay. Let's try this. So we partition our real number line into intervals. I can count the intervals. I can take on the positive side and the negative side that region, in this case, between 0 and 1. All right, that's good. You can absolutely count these. Then, for each region, I'm going to chop it up. And I can absolutely chop it up in an uncountably infinite number of ways. All right, I can say 0.1, 0.11, 0.12, 0.13, and I can keep going, okay? So absolutely, I can chop up one of these countable intervals between consecutive integers on the real number line, and I can chop that up, okay? Now, I can do even more. What if I take the space between two of these smaller intervals? I can chop it up again, 0.0001, 0.0002, and I can keep going, all right? But you'll find for each partitioning, you can partition it again, and partition it again, and partition it again. And an infinite number of times, you're going to keep subdividing and subdividing and subdividing and keep going on an infinite number of times making those subdivisions. And even then, you never get to the individual elements of the set of reals. That's what uncountably infinite means. This infinity is so big, you can't even list out and number the individual elements of this set. Any questions about that? Does that make sense? And I swear, this is sort of anecdote. When I was in high school, I took calculus in high school, and it was beautiful, and I loved math. And then I went to engineering college, undergrad, and they sucked the joy out of mathematics. So hopefully they don't do that here. I hear that they're pretty good in the math department, but I promise you, go to grad school and take a graduate math course, and they'll pump the joy back into mathematics for you. But I digress. I have some very strong opinions about that. So this infinity is so big that you can't count it. That's what it means to be uncountably infinite. That's really, really big. So let's remember what the law of total probability says. It says if we have our universe of consideration and we talk about probabilities, the probability of all the possible objects in our universe of consideration, if you sum them together, it sums to 1. If you want to casually put it, something's going to happen, right? Something, right? So recall that, and let's talk about uncountably infinite. Now, this is an absolute abuse of notation. I can't count them, so I have no way to talk about them. But I need to have something on the slide. I can't have a blank slide and say, this is uncountably infinite, right? That doesn't make sense. And so and this is an abuse of notation, and this is mathematically incorrect, right? That's why I have the diagrams of peanut butter on the board. So if I were able to list out the individual elements of the set, I could sum together their probabilities. And if I could do that for real numbers, even though they're uncountably infinite, you can't really do this, I add them together, I get 1, because that's what probability calls for. That's one of the basic rules. Okay, so I have a fixed amount of probability mass, 1 unit. I spread it or scatter it out among all the elements of the set, in this case, the set of reals. Let's look at what happens with a jar of peanut butter. I get a big, nice, generous glop of peanut butter. I open the jar, and my dog always knows the sound of peanut butter jars opening. You know, you open the fridge, open the peanut butter, turn around, and my dog's there, right? I don't know what happens. It's kind of out of nowhere. But you get 1 unit of peanut butter. Doesn't matter what it is. And now you take that unit and you want to spread it out on your bread. Now let's define this one. In this case, you have a really long piece of bread, right? Maybe you take like some scaly bread or some French bread, get a really nice long slice of bread. If you have that unit of peanut butter and you fix that unit of peanut butter, you're going to have to spread it very thin in order to cover all the bread, okay? In this other case, let's say you get a short piece of bread, right? You're not that hungry. You have that same unit of peanut butter, and this unit of peanut butter with a shorter region, you're going to spread it more thickly. Now, one of the interesting parts is when you spread it, you can measure this idea of thinly spread or more thickly spread. And how you measure that is by taking the amount that you have over some span or some region, right? And so we're going to work with that idea of regions. And the other thing that's very interesting is that when you spread the peanut butter, let's imagine the envelope or shape that peanut butter makes as you spread it out. Let's consider that as a function. Now you can make tools or use tools of calculus to add up all of this peanut butter over your region. And so it's the Riemannian sum. And essentially what it does, it says, okay, let's take little tiny sliver rectangles and let's add them up. And that rectangle is really, really, really narrow. And if you do that narrow enough and add up the rectangles, the area, well, we know the area of a rectangle is width times height. The height is that function representing the thickness of the peanut butter at that point. And the width, you can make arbitrarily small. And so by adding up these rectangles, the so-called Riemannian sum, you can actually get a good approximation of how much peanut butter exists along that run over which you're spreading it. Does that make sense? Okay, any questions? Now, the issue is, if you spread your peanut butter over a large number of things, essentially for one particular part or unit of peanut butter, you get the limit 1 upon n as probability, which is 0, because it's very many of them. Does that make sense? And so, oops, you broke your probabilities. For a real number, the probability of any individual number is 0. So how can we talk about probability of temperatures and pressures and things like that? What instead we're going to do is, instead of considering individual elements of the set of reals, which you can't do, it's uncountably infinite, we're going to take the amount of probability mass, the amount of peanut butter that's spread across a region of the values in the set of reals. Does that make sense? Any questions? No? All right. And so what does it mean? If you have a value from the set of reals, the probability of that value, if you could identify it, is equal to 0. Okay, if you could count it, I mean to say. So you broke your probabilities. This is one of those oops moments. So what did they do? Instead of talking about the so-called probability mass function, they talk about the cumulative distribution function whenever you traffic in real values, or the CDF. And what the CDF does, it says, like our Riemannian sum, how much peanut butter have we spread from the left extreme, minus infinity, to the right extreme, positive infinity, for that way you're spreading the peanut butter. Now, of course, you see here, the peanut butter is thinly spread, roughly the same amount from left to right. Here, the peanut butter kind of gets thinly spread and then increases to really thick and then drops off back thinly. So the way in which you spread your probability mass can be different, and those correspond to different densities or density functions for real values. Does that make sense? All right, so instead of talking about the probability of an individual element of our set of objects from our universal consideration, we talk about the cumulative probability, the amount cumulative across our universe of consideration. Now, the word is called the support set, right? We've been calling it universe of consideration, but the real word is called the support set. Okay, does that make sense? Any questions? Now, because it's real valued, now we need a way similar to a mass function to talk about regions along the stretch over which you spread your probability mass. And so the so-called probability density function is the first derivative of the cumulative distribution function. And what that density function represents is how thickly spread or thinly spread your probability mass is in some region over your support set. Does that make sense? Any questions? No? All right. So so-called continuous or real valued random variables like temperature, pressure, distance, velocity has a so-called probability density. And if you read a statistics, yeah, that sounds like a superhero, statistic. Anyways, um, if you read a statistics book, the quantities that you need to describe any real valued probability distribution, you need the CDF, cumulative distribution function. You need the density, which is the derivative of the CDF. And then you also compute the summary statistics, the mean and the variance. And calculus gives us the tools in order to do that. Okay, so let's go back to this idea that we had of partitioning the real number line using regions marked by the integers in positive and negative infinity. So you can't talk about the probability of a single real number. You talk about the density of how you spread it at that point along the span. But you can take an interval and using this idea of how you spread over the region, you can absolutely talk about that probability. So here's an example. Holness, I don't believe you. Here's an example. We know that we have our real number line. It goes off into positive and negative infinity. So I'm going to take the value 0, which I absolutely can identify from the integers, which are whole numbers, positive and negative, including 0. And I'm going to define a region goes from negative infinity through 0. And then I'm going to define another region. It goes from 0 to positive infinity. Now, these regions are both on the real number line, and they precisely partition the real number line into 2 equal regions. And if I spread my peanut butter, my probability mass, equally over both regions, I know that half of that probability is on the left-hand sector, and the other half is on the right-hand sector. I only have 2 pieces. I can even identify the 2 pieces. First piece is the left one, second piece is the right one. Knowing law of total probability, I have 1 unit of probability mass. Half of it is on the left, half is on the right. So the probability of each of these sectors is 0.5. Even though it's a real value, the idea of considering regions over which mass is spread allows me to traffic in probabilities in spite of this number line being uncountably infinite. Does that make sense? Any questions? No? All right. So each interval has half of the values. And calculus, when we're talking about the summary statistics, calculus gives us the tools, the definite integral and the indefinite integral that we can use to add up these sliver rectangles. In fact, the definite interval is just the limit of the Riemannian sum. You take these rectangles, you let the width of them, delta x, get really, really small as delta x goes to 0, and this becomes precisely the definite integral. And if you talk about that with your calculus teacher, this person, tear will run down their eye. Oh, so beautiful, this stuff. All right, any questions? And I have some sources there if you're interested. No questions? No? All right. So let's see. We have about 13 more minutes. Let's take our first version of our continuous distribution. And this particular distribution talks about smearing our peanut butter or our probability mass the same thickness everywhere over which you're going to smear or spread your probability mass. This is a so-called uniform distribution. And the uniform distribution gives equal probability or equal density, I should say, to all of the, and I would say peanut butter and probability mass as synonyms in this kind of weird way of talking about it. But the uniform distribution corresponds to stochasticity in a real valued quantity where the probability or peanut butter is spread evenly, the same thickness everywhere across the support set, across the bread. Does that make sense? Now, remember, when we talk about probability, we assume between minus and positive infinity. But just because you talk about minus and positive infinity, it doesn't mean that your density is going to place peanut butter there. For the uniform distribution, it only places our peanut butter between two bounds. On the left-hand side, it's A. On the right-hand side, it's B. Everywhere else, it's 0, right? And so this particular density function has chosen only to spread the peanut butter, to work with that analogy, in this region. Let's call that A on the low side and B on the high side. And so I'm going to insert here. You could choose to have a big piece of bread here, and let's say A is here, B is there. That means your peanut butter is evenly spread only on that region of your bread, right? Everywhere else it's 0. So it's really important to note each one of these different stylized family of distributions for real valued variables, it smears the peanut butter differently in a stylistic way. Any questions? No? And so for the uniform distribution, you can look up the CDF. The density function, f of x, is 1 upon b minus a. And it's only defined anywhere between a and b on our number line. Everywhere else, it's 0. Okay. So if we look at the expectation, it's a plus b over 2. And for the variance, it's b minus a quantity squared upon 12. And I can certainly post links to derivations if you're interested in that. I'm not going to hold you responsible for the derivations in this class. If you take a DSCI 216, I think I'm going to go over derivations there. Okay. Any questions? Does that make sense? So now let's look at the exponential. And we'll probably end with this. We have about 8 more minutes or so. And so we talked about the Poisson distribution, and the Poisson traffics in counts, the probability that we observe k many events arriving in time, delta t, given an average rate lambda. And so what happens if our event is so-called rare? That means our rate is smaller. One of the quantities of interest, I jumped ahead, is the time. All right, I wasn't expecting this. A very small rate corresponds to a relatively rare event. And so the Poisson distribution, that's where my mind was going. For this slide, the Poisson distribution tells us the number of events per window of time. And one of the quantities of interest would be the so-called inter-arrival time, the amount of time between the observation of some event. Now, time, as we said, it's real valued, it's continuous. And so we need one of our continuous distributions. And this is exactly what the exponential distribution gives us. It answers the question, what's the probability that this is the length of time until we see our next occurrence of an event, the so-called arrival time or inter-arrival time. And so this particular type of density for the exponential distribution, it talks about spreading our peanut butter in a differently stylized way. In fact, the exponential distribution draws its name because it's a decaying exponential curve. And you can control how quickly it decays or how stretched out that decay is. And what the exponential distribution says, all right, I'm going to smear peanut butter with the assumption that it's going to start out very thick and it's going to get very, very soon and very, very thin, and it's going to change how thickly, how it thins out over that span over which the peanut butter is spread. And so this is the density function for the exponential distribution, and there's absolutely beautiful relationship supported by proof between the exponential and the Poisson. It comes from that. It's the inter-arrival time between events. And so for the exponential distribution, there's no such thing as negative time, right? Well, maybe if you're a quantum physicist, they'll figure it out one day. But in this class, there's no such thing as negative time. And so for this type of density, It says, I'm only going to smear the peanut butter on parts of the bread that are greater than 0. You can't have negative time in this case. Does that make sense? All right. Any questions? And so to get the mean and the variance, you just use integration. I won't go over this derivation. I'm more than happy to point you either to my own modules with the derivation or someone else's. I can certainly make that available on the Moodle, on the Canvas site. And so here, this is our expectation, 1 upon lambda, where lambda is the rate. And then this is our variance. Now, there's another way to compute the variance using the so-called variance equation. The variance, we said, is equal to, in this case, because it's continuous, the integral from minus infinity to plus infinity. We take our variable, it's a real valued, and we subtract it from the mean, quantity squared, and then we say P of x, our density function, more correctly, I should say f of x, to be consistent, dx. Okay? All right. And so this is one way to compute the variance. Another way is through the so-called variance equation. And I can certainly give you a module on that I've recorded for a different class. But the variance of an exponential distribution is 1 upon lambda squared. Okay. And for this, you're going to use integration by parts. And I can certainly point you to sources on that if that's of interest to you. But we're not going to go through that in this class, and I won't hold you responsible for the derivation. It would just take too long to go through all this stuff, given the data science topics that I have planned. All right. Any questions? No? So it talks about time. Anytime you're going to model something that deals with time, it's going to be the exponential, except if you have a special sequence of time. And we'll talk about that in a moment. And so, you know what? Let me not push it too hard. We have about 6 minutes. And just to set up for the gamma, it belongs in its own thing. So I don't want to break it between today and next time. So why don't we stop with the exponential and we'll pick back up with the gamma. And then my favorite thing is essential limit theorem, right? It's this really cool thing that allows you, regardless of what the stochastic structure, you can morph it to something else. And now you can make comparisons between those two things, two variables that at the end of the day were entirely different, right? And that's CLT is one of the fundamental results, at least for probability. All right. So with that, we're going to end here a little early. I don't want to break up gamma. I don't want to push it too hard. So let me stop the recording, and I'll see you all on Wednesday.